It is a distinctive privilege to introduce Professor Dr. Carl Wieman. Dr. Wieman serves as Professor of Physics and of the Graduate School of Education at Stanford University. His scholarly work includes extensive experimental research in atomic and optical physics. In recent years, his academic focus has centered on improving science education, particularly at the undergrad level. He's been instrumental in advancing the use of empirical methodologies to assess the effectiveness of instructional practices in physics and related disciplines. Moreover, he held the position of Associate Director of Science at the White House Office of Science and Technology Policy. We are truly honored by his presence at this conference. Today, he will present Taking a Scientific Approach to Science and Engineering Education. Please join me in welcoming Dr. Wieman. Come on. Dr. Wieman, you have the floor.
Okay, thank you. You can see my slides all right?
Yes, of course.
Okay, yeah, so this is going to be a big change in topics. I'm going to talk about education and taking a scientific approach to it. Now, education systems across the different countries vary a great deal in their details, but I'm going to try and cover basic principles we've seen that enhance learning that could apply quite generally. And so, but the data is coming from North America in particular. I think we have some data and some good reasons to believe that they'd apply in Peru as well. Now, first, I just want to give a general overview, which is that although I don't think we should expect or try to turn all students into scientists, it's important to give a basic scientific literacy for all students, because this is just a way of thinking that'll help them make better decisions in their personal life and their jobs and societal policies. Now, the goals of this talk are for teachers to give you insights about teaching and how to do it better, and for their students in the audience, it's really give you an idea of what you need to do to learn better. And so I've organized the talk in terms of first a general introduction about how the brain learns complex thinking and a new way to think about this, and then focusing down, applying these ideas in the university classroom and measuring the results, and then go into more details about what research shows specifically improves learning and why. And then I'll finish with a few remarks about the role of artificial intelligence in education. Now, over the past few decades, there have been major advances in research that give new insights on how to learn and teach the complex thinking like a scientist or engineer. And it's come from three different complementary fields. There's the cognitive psychologists who study the basic processes of thinking and learning, usually in laboratory settings, brain research, and then people like myself, faculty in physics, biology, etc., who are carrying out experiments in university science and engineering classrooms, trying different ways of teaching and measuring the results. Now, the best data, and most of the data, comes from North American universities, and so it's a reasonable question as to whether this applies more broadly. And I think, as I said at the beginning, there's some sort of general principles that come really from studies of basic human learning that give you reasons to believe that. Also, we are getting increasing amounts of research from around the world that show that the ideas are quite consistent. So let me start with sort of one of the most important ideas from research is really rethinking how learning happens. And the old and still very pervasive model in the university system is that these student brains that come into our classrooms, they vary in different ways. We immerse them in knowledge, giving them lectures, and that soaks in to different amounts depending on the conditions of those brains. And so the focus is then always on selecting the best brains, by exams and so on, that'll absorb the knowledge best, and deciding what to put in the knowledge soup, what to give what topics to cover in the curriculum and what order and so on. Now, although this is a very long held and still widely held belief about learning, it's basically just wrong. And what research gives us is quite a different view, which is these brains, at least at the university level, aren't very different, but they're quite changeable, in fact. And the education process really transforms the brains. Literally, it changes the, how the neurons are hooked up so that they're rewired in response to the intense thinking that the brain does during learning. And this is really developing. This rewired brain has improved capabilities. So it's really about developing brains rather than filling them with knowledge. And you can even see this effect in modern brain imaging. This is the brains of two people who are in MRI machines, and they're while interpreting X-ray images. And on the right is the brain of a medical student who's just learning how to do this. And on the left is a highly trained radiologist. And you can see how their brains are activated in completely different ways in carrying out this task. And so one implication from this is these high stakes exams that really determine a learner's future are quite problematic because they really reflect past educational privilege, not the future capabilities that the learner might be able to attain. So what we see is really the brain learns, it develops through practice. And so, this practice of the thinking to be mastered is really critically important. And so this raises the question of why has this not been more widely recognized? Because I think almost anyone would think that to become a highly skilled musician or an athlete, you couldn't possibly do that just by listening to someone tell you how to do that. But for a long time, people have believed that become a skilled scientist and engineer, you could just sit and listen to lectures. And so part of the reason I think is that the level of performance is much easier to measure in music or athletics. So you can see immediately what kind of training, what kind of teaching is more effective. And so people have come to recognize the importance of practice rather than just telling people how to do something. And so in things like thinking, like a scientist or engineer, that's a much more difficult thing to measure. And so it's led to people being able to have these wrong ideas about learning and teaching for so long. But in recent years, there's now much more research on actually measuring the thinking, and this is giving us then data on better ways to teach. And that's really what my whole talk is about today. So the first is that basic brain research tells us that learning is enhancing the relevant neuron connections, and the brain learns what it practices. And so it's much like muscle development, that the intensity and type of exercise is critical. And this is true for a muscle, but it turns out it's similar true for the brain. Now, but through research studies, researchers are continually learning more effective ways to teach and learn, what sort of practice to have the brain do to develop new skills better. And so just to summarize then, to move on of what the learner needs to do, and this really is true for expertise in any subject. And the point is that it requires a particular kind of practice of the desired thinking that makes up the expertise. And this is work that's really been pioneered by Anders Ericsson. And he's seen that this very important kind of practice has certain components. First, it has to be very intense. The learner has to be fully concentrating, not just kind of doing routine practice or experience. It has to be focused on improvement, particularly the particular sub-skills that make up the area of expertise you're interested in. And the practice, you need to be practicing what you want people to learn. So in science and engineering, this is primarily sort of solving problems and figuring things out. And it's very important that the practice be challenging so that the learner is undergoing practice tasks that are very difficult for them. Hopefully not completely impossible, but if one lesson that learners and teachers have to learn is that if it's not difficult, then the person really isn't doing very much learning. And so it has to be very challenging. And that means sometimes students are going to necessarily fail. Now, just practicing in a challenging way is important, but it's not enough. The learner has to have feedback on what they're doing right, and most importantly, what they can do to improve. And so then you need to just have this cycle repeating itself of practice and feedback, more challenging practice, more sophisticated, complex practice tasks, more feedback, and so on. And over time, the brain develops and acquires expertise. But one thing that the research has also shown is that motivation is very important in this, and that serious learning is necessarily hard work, hard mental effort. And so the learner has to be willing to put in that work, and the teacher has to be willing to think hard about how to motivate learners to put in that effort. And one of the things that Ericsson's shown in his research is that beyond the very beginning stages of acquiring expertise in some area, the quantity of this high-level, intense practice, so the educational quality, if you like, really determines performance level. And that things like what you might try and measure of ability or talent, those really don't have much effect. That it's really the high-level practice that dominates learning. So this is really a brief summary of what the learner needs to do to master a subject and what a good teacher needs to facilitate. Now, I'm going to move on to talking about now applying these ideas in university classrooms and measuring the results. And I've done this experiment now for many different science and engineering courses and getting data showing the improvements. And I'll just give you a couple of examples of this. So this is an example from a very large introductory physics class where you could identify two sections of 270 students each, which were essentially identical student populations. And then the experiment was to teach these students in these two sections in two different ways. The control section was taught by a highly experienced professor with good student ratings, but he taught using the standard lecture approach, talking to the students and they'd listen. The experimental section was taught by somebody who was a new physics PhD, trained in these principles and methods of research-based teaching in the program I ran. And so these two instructors agreed to cover the same material in the same amount of class time, and then give us a surprise exam to both classes afterwards to see just how much they'd learned from these classes. So I assume you're all familiar with how the lecture approach works. The experimental class is somewhat different, though. So let me explain first, there was a short pre-class reading assignment that would give students sort of basic facts and terminology. And then during class, they'd have to have tasks answering questions. So for example, this is example of one question that they're given a circuit with a battery and light bulbs. And when this switch is closed, they have to predict what's going to happen to the brightness of bulb number 2. And they give a set of choices. Every student here has at the time this was done, was a clicker, a dedicated device that allowed them to make a choice. Nowadays, that's largely replaced by mobile phones, but in the same principle is the same, that every student can then individually answer, and the instructor's computer records who the student was and what answer they chose, and can see the distribution for the whole class. Now, after the students have selected an answer, they're not actually told what the right answer is. Instead, they're told to discuss with their neighbors what the reason is and why, and re-vote. And while they're doing that discussion, the instructor's circulating around, listening in on those conversations, getting little snapshots of what thinking is going on in the student's brain. So what aspects are thinking like a physicist like you want, and where they're going wrong. Then there's a demonstration to show what the result actually happens. And then a very important component is there's a follow-up summary from the instructor, which really focuses on giving feedback to the students on which models and reasoning was correct and which were incorrect and why. And I particularly emphasize the incorrect and why, because that's really where most learning takes place, when you realize something aspect of your thinking was wrong and how to change it. Now, in a course like this, not everything could be done with multiple choice questions. So students have other tasks where they have worksheets were more mathematical. They have to write out explanations and solutions, but again, in discussion with their fellow students while the instructor's monitoring what they're doing. So if you think about what the students are doing in this class, they're practicing thinking like a physicist. They're having to choose and apply a conceptual model of electricity, and when they're doing this, they're also critiquing the reasoning, both of themselves and their fellow students. And while they're doing this thinking practice, they're getting feedback from multiple sources to improve it. They're getting it from their fellow students in the discussion. They're getting it by comparing their predictions with what happens in the demonstration, and they're getting it from the informed instructor. Now, so that's how the experimental class worked, but I told you this is part of an experiment. So there's a surprise quiz given in both sections of the class. And this is the results of this, with the test score on this axis and the number of students on that axis. And you can see the experimental section scored much higher, showed much more learning. And in fact, if on this particular test, random guessing would give a person 3. And so it's sort of amount of learning is how far above 3 are. And that shows you that the lecture class, the learning was really tiny, and this is consistent with other studies we've done. But it also showed, the other thing I want to emphasize is that the blue distribution, the entire class distribution is moved up. So this shows that this isn't something that's teaching that's just more effective for the weakest students or the strongest students. It's really more effective for all the student population. Now, that was an example from introductory physics. This is an example from another subject, computer science, looking at a different measure of learning. So this is the 4 core computer science courses taught at University of California at San Diego. And here they're looking at the drop and failure rates over the whole courses. And this work done by Beth Simon, who collaborated with me for a while. And here you have the same 4 instructors, but they taught the standard lecture approach 1 year, and then they all converted to this scientific teaching the following year, and based on very much just like what I described, of giving students questions, they have to answer, they discuss with each other, get feedback from the instructor. And then, so that was the second year, and they could look at their drop and failure rates, and you can see across all these courses, the drop and failure rate went way down. And so you have an example here that the same 4 instructors, they're simply adopted better teaching methods, and now they have about 1/3 the failure rate they used to have. Now, most of the research has been done on introductory classes. That's where most of the more students are, and just been history. My group and a few others have been looking at applying these ideas in more advanced courses, particularly more advanced physics courses. And we've seen that applying the same ideas gives we can collect data showing a large amount of improvement over the lecture teaching as well. And so, in fact, that nearly all of the Stanford undergraduate physics courses have now been transformed to this kind of teaching. And see, these are smaller, much more mathematical classes, and so the students are almost always working on worksheets, writing things out, while the instructor is still wandering around, monitoring how they're doing. And so, in fact, the structure of these classes is shown here, and this is a structure we've seen works pretty well for just about any subject and course level and class size. And the basic idea is the students do some sort of modest preparation for class. The instructor creates these practice task activities for the students, introduces them to the students, and then the students spend most of their time working in these small groups, working out the worksheets, the set of activities, while the instructor is circulating around, occasionally answering questions, but really monitoring what the students are doing, listening to how they're thinking. And then periodically at appropriate times, the instructor will bring the class back together and give them feedback on what they were doing, sort of bring everybody up to the same level, and then the groups will go back to work on the next portion of the activity, and just continues to repeat the same way throughout the class time. And so the 2 sort of essential features here is that the students are busy thinking, they're practicing the expert reasoning, thinking you want them to learn, and the instructors are much more knowledgeable about that thinking, so they're able to do more effective teaching. So those are just a few examples. There's I've been able to tabulate nearly 1,000 research studies across fields of science and engineering that are comparing sort of the traditional lecture with this kind of research-based teaching. And the research-based teaching consistently shows greater learning and lower drop and failure and dropout rates. Now, I should say we only have data from science, or almost only from science and engineering, but the ideas likely apply to essentially all subjects like math, economics, etc. So I'm going to move on now to go into more details about what research really says about works to improve learning and why. And this is sort of gives you more details about what things one can do as a teacher. And so this slide sort of represents all the areas of which their research on teaching and learning. And so there's at the heart here is sort of learning, the practicing in science engineering. This means practicing solving authentic problems and with good feedback. And good feedback is feedback that's timely, specific about what to be done, and actionable, so the learner knows what they need to do to improve. But then there's a bunch of different areas covered up here. That's research on what's important to making the design of the practice problems to be effective. And there's research on, down here in these boxes, on implementation to make this, actually implement these ideas effectively in a classroom. And so all of the things really contained in these boxes define teaching expertise in a way that I think you couldn't have done, 20 years ago. In that these show practices that research shows consistently produce more learning. So I don't have time to go into detail about all of these, but I'm just going to talk about a few. And I'll start with the disciplinary expertise. What's kind of the important thinking that needs to go into science and engineering practice here. And this is an area in which the research from my own group has provided, I think, some useful guidance here. And we looked at how a whole bunch of experts across science and engineering and including medicine solved authentic problems in their field. And we found that their problem-solving process was defined by making a specific set of decisions with limited information. And the thing that was most striking to us was across all these different fields of science and engineering, we found the same set of decisions. And so, that was really unexpected, that their problem-solving process involved a consistent set of 29 decisions that they used almost all of them solving any serious problem. Now, that may sound hard to believe until you actually look at what these decisions are. They're things like just, when they see a problem, deciding what concepts or models are relevant, deciding what information's needed to solve the problem and how to get that information, deciding what approximations and simplifications are appropriate, deciding how to break the problem up into pieces. Once you have information, deciding how credible that information is and what conclusions can be drawn from it. Once you see the decisions this way, you realize it's much easier to believe that, yeah, these are going to be useful for solving a great variety of different problems. Now, here's the list of problem-solving decisions, and I'm just going to give a minute for you to read through these to get a little better idea what's involved in them. And I'll talk in a minute then about why I see these problem-solving decisions specifically are so important in the actual learning process. So I'll just stop talking for a minute here and let you read.
Okay. Thank you, Professor Wieman, for sharing your knowledge and.
I'm sorry. I'm going to go further here.
Okay. Yes. Yeah.
I have more
Go
to
ahead.
say.
Go ahead. Sorry to interrupt you. Go ahead, Dr. Wieman. Go ahead.
Okay, you probably haven't got through all of them, but you've seen several of them, so you got some idea. And I want to say, although the decisions are general to all these different disciplines, making the decisions is quite different. It always requires specialized knowledge appropriate to that context. And we see the experts have their knowledge organized really around the use of making decisions. And so they're learning, not just learning knowledge, but they're learning why and how it's useful. And so this tells us that the best way to teach knowledge is really in the context of how it's to be used. And so learning good expert thinking at all levels, I would argue, to summarize, is this extended practice at making problem-solving decisions using the knowledge and reasoning of experts. And so if you think about these decisions, we want students to learn to be good problem solvers, but technical problem solving is a very complex task involving many different ways of thinking. And you can think about these decisions as sort of little pieces that make up the problem solving. And so it's a much more efficient way if students are working on having to make just specific decisions instead of all the problem solving at once. Now, one of the things we've done research on is comparing the learning if you are treating two different ways. One is you have the students actually practice making the decisions versus a lecture like usual teaching in which they're just told what the decision should be, what the solution should be. And doing this comparison, we found enormous differences in learning that the students who actually practiced making the decisions were much better at making relevant decisions in future problems. And the other point I want to make is that most of these decisions that are always needed for authentic problems are removed from very typical sort of textbook and course problems so that the students learn information but not how to use it. And I'll just give a little bit example about if you think about first, here's a set of 5 decisions that are sort of necessary for any kind of reasonable problem a person would have to solve, recognizing relevant information, justifying assumptions, what concepts apply, and so on. But then you look at a typical problem that students are given a textbook or exam. First, all the information needed and only the information needed to solve the problem. So that immediately takes that decision, is removed. They're told what to assume, what to neglect, error resistance, and so on, takes away that decision. Very often they can just solve the problem by plugging into the equation or procedure from that week. So that takes out the decision of what concepts apply. They only call for one representation, so that takes out moving between thinking about what specialized representation to use. And they never have to sort of justify their answer. They just give a solution. And so that takes out. So this is just an example of how conventional class problems can so often remove all the decisions that it's really important students to practice and learn. Now, we've actually gone to providing students with a problem-solving template that they should follow that involve a subset of these decisions. This is used in actually 5 different Stanford courses and now adopted this, where there's a certain set of decisions they involved in framing the problem, thinking about problem, what it's asking them really to do, and formulating clearly in their own mind, and then a set of decisions that have to plan the solution and working on a plan of what they're going to do, deciding what concepts they'll be using, what information they need, how to get that information, etc. And then it's more straightforward, the executing the problem, and then reflecting on, does the answer make sense and how to test it? And if so, if not, how does one go wrong? Like I say, we adopted this for one course, but it has been seen so valuable, it's now been picked up in many different courses at Stanford. here's an example of kind of an authentic real world problem we've given that students to solve that gives them more authentic decisions that they have to make. And this is just the problem with a dresser and student and children climbing up on the drawers and tipping it over, and that the student has to calculate how strong a wall anchor you need to hold this. And so there's a whole bunch of things the students have to decide: what assumptions they apply, what concepts apply, what information they needed, and how to get it. All these things of kind of real world problems. Okay, I'm going to skip over the prior knowledge and experience. Just the practice problems need to address that and be relevant to that, and motivation. These are kind of obvious what's involved in this, but it's one of the most challenging aspects, that there's variation, student variations a lot in both of these. And instead, I'm going to just jump to a basic brain constraint, which is important. This is how the memory works, but it's quite relevant to teaching. And if you look at the memory way cognitive scientists do, they talk about it as really having two components. There's the long-term memory, which is most of us think of as memory, which is large capacity and long duration. But then there's another component that's not usually thought of, which is called the short-term working memory. And this is kind of a buffer that information has to go through before it can be processed and into long-term memory. This works on a short time scale, minutes, and it's got a tiny capacity, typically 6 items, the human brain. So it's really what the brain can pay attention to at once. And because of this very limited capacity, when the brain hears or sees something new, gets some attention, that pushes out something that was already in this working memory. And so that whatever gets pushed out is kind of lost. It never gets processed. So the important implication to this from teaching is that any additional item that one introduces in teaching that draws students' attention, that reduces the learning process. And so everything that uses attention has a cost. And so having your students split their attention by looking at computers or checking their cell phones, that just makes a disaster in their learning. But things that the instructor does that kind of add extra demands on their working memory, like jargon, too many topics, even pretty pictures or interesting little digressions or jokes, they're sort of separate from the learning that you need. Those actually hurt the learning. Okay, let me just jump through the implementation a little bit. One thing we've seen is that these tasks given to students need to have clear deliverables, something the student has to complete. The other point I want to emphasize, the social learning. We've seen over and over again that the best research-based learning has students work in small groups in class, typically 3 to 4 students. And a lot of instructors, when they first hear this, they have trouble believing that talking to fellow students can be better for learning than listening to an instructor explain something. But the fact is, it is really better, and it's for several reasons. One is that fellow students can provide more individualized feedback than an instructor ever can in a large class. But more importantly than that, there's some specific cognitive processing relevant to social interactions, so that teaching or explaining something to others, or actually just planning to do this, actually brings in unique ways of thinking that actually support learning better than just studying it. And so it's a very interesting field. And then it's just useful for a teacher to listen on those student conversations. Okay, I'm just going to spend a couple minutes on the role of artificial intelligence in education and finish up here. this really raises two questions. What should students learn in the age of artificial intelligence? And how can AI help teaching and learning? And the answer to the first question is, I just don't really know. I mean, I think scientists and engineers are still learning how to best use a tool, AI as a tool to support authentic problem solving. And so we're just going to have to look and see how this is done in future years and teach students to work like AI, how they do this. My guess is that we're still going to need human reasoning for novel problems, these sort of good judgment about decisions where there's limited information. I think AI is good for providing knowledge. It's not so good for making judgments. The second part about using AI in education, my group has been studying this, trying to see if we can make an AI tutor. And there's potential there, but it's really not as easy as most people think. At first, it's sometimes wrong, but more importantly, that's really designed around giving solutions. And that's just giving a person the right answer is not a very effective teaching. You need to give them feedback to help them develop their own thinking. And so what we've seen is you need a lot of human intelligence to guide the AI to make it more effective. Now, there is a different form of AI, which is different from the large language models, that has been shown to be clearly effective. And that's these interactive computer simulations, which is the FET project now has 167 of these. They're in all different languages, including Spanish. And these aren't language models, but they're artificial intelligence in the way that the student takes action and the simulation responds based on some algorithm. And we see there's good data showing they really help students to get better conceptual models of physics and other science concepts. And so this is just an example of one of these with a circuit construction kit where students can take different components and they can build circuits like I've just done here, and they can see when they make a complete circuit, it makes the electrons move, the light bulb lights up, they can change voltage and so on. So there's simulations like this for all different topics of math and science. And like I say, they're quite effective. So I'll just finish now with just kind of emphasizing that research is now showing us good design and implementation that gives better learning than our traditional lecture process, and we understand why. And here's some references if you want to learn more about this. I'll make sure my slides are available somehow. Thank you. So now I presume there'll be questions.
Okay. Thank you, Dr. Wieman, for sharing your knowledge with us. Now, I kindly ask you to stay with us, Dr. Wieman, after the panelists' questions, as we have something important to share with you, okay?
Okay.
Please don't go, okay? Okay. Now we have three panelists this afternoon. Our first contributor is PhD degree Avelino Vicente, a faculty member of the University of Valencia in Spain. He will address his question directly to Dr. Wieman in English. Dr. Vicente, are you there?
Okay. Yes, I'm here.
Oh, yes, you may begin. You may begin. Go ahead.
Okay, well, first of all, thank you for the presentation, Dr. Wieman. It was a fantastic presentation. I really enjoyed everything you explained, and I'm now thinking about how to implement all these ideas in my own teaching in Valencia, in Spain. I would like to ask you about active learning, which is something that you have argued in favor during your talk. We have found here in my university that some students have some resistance to active learning, like they are not used to this intellectual effort during the lectures. So my question would be, have you found anything similar? And does active learning work out of the box, or do you need any adaptation time? Thank you.
Yeah, so the answer is we have seen, I led this large science education initiative, which changed the teaching of many hundreds of faculty, many hundreds of science classes. And there's no question that there is some student resistance, so that if they're familiar with the form of teaching, they're much more comfortable using it. Like in Stanford now, the physics students, they would probably object if you just lectured at them because they're so used to active learning. But what we found in our work was that there was some student resistance, but that if you really needed to take some time to sell the students on the active learning. And the key ideas to that were to first sort of give them research showing why it was being done and why it was done, it would benefit them, and that they weren't just experiments in your, they weren't just lab rats in your experiment, that you had some real justification for doing this and it was for their benefit. And, I'll say that doesn't immediately convince all the students, but it greatly reduces the resistance. And then over time, as students realize they're learning more, they're getting more out of class, then the attitudes also improve. But you can't just do it without giving them any warning as something that's just completely new and unfamiliar, because they will be uncomfortable with that.
Thank you.
All right. Our next panelist is a PhD degree Juan Carlos Gonzalez, a professor at the National University of San Marcos. Dr. Carlos Gonzalez, are you there?
Yes, can you hear me?
Okay. He will likewise present his question in English. Dr. Gonzalez, you have the floor is yours. Go ahead.
Many thanks, Professor Wieman. Many thanks for your excellent presentation. I have two questions. One is for the Professor Villegas, and the other is mine. What happens when the results are not as expected? How do you improve the indicators when the results obtained are not the best in the active learning?
I'm sorry, you spoke a little too rapidly.
Sorry about that. No, I'm talking about when the results are not as expected. The results you obtain about the indicators. How do you improve your indicators? When the results obtained are not the best.
Oh, you're saying when the results are not as good as you hope?
Yeah.
Yeah.
Yes.
Okay. Yeah. So,
some tips about that.
Yeah. So, in that regard, I would say it's just like in doing my traditional physics experiments. You look carefully at what all the reasons are, and you try and figure out what you need to do differently, and you rely on what you know as basic principles about what things, and the principles at this point have been pretty well established, or quite well established, and so it's always it's other factors that you didn't take into account, you overlooked. And like I say, whether it's a laser experiment looking at atoms or working with students, you have to use much the same sort of reasoning. But one key thing is you can, a lot of cases, it's just a question of asking. But you have to use kind of very careful, structured ways of talking with students to understand their thinking. And usually when it's working less well than you expect, it's because some rational reason that they had, what they were doing was different than you thought, and you just have to then think about what you have to change to address that.
Many thanks, Professor Wieman. And on behalf of Professor Villegas, Dean of the Faculty of Science Physics, he asked, in the near future, what methodologies will be used in the teaching of physics, and what is expected from the introduction of artificial intelligence in the teaching of physical science? Sorry, sir, very long.
You know, I think that the method still you know, I'm assuming that we're thinking about in the future where we have artificial intelligence, that a lot of what we teach of knowledge is, you know, people can just look up. And so you're not going to have to teach that. My feeling is you still need them to practice essentially making these judgments, because those are things that artificial intelligence isn't so good at, making judgments when there's limited knowledge, and especially in novel problems, which, you know, haven't been solved routinely before. And we see this when we give students more realistic, authentic, real-world problems. The artificial intelligence is not nearly as good at solving those as it is the kind of simplified artificial textbook problems. And so, you know, my feeling is that there's, for the foreseeable future, the best thing to do would be to give students authentic problems and they have to practice solving them, making these problem-solving decisions and judgments in the process, and that will be valuable for a long time.
Many thanks for your answer, Professor Wieman.
Okay, now we have our Dean of the Faculty, Dr. Maria Natividad González Segarra. Are you there, Ms. Dr. Segarra?
Thank you. Professor Carl Wieman, thank you very much for your inspiring and insightful lecture. It has been a true honor to learn from your work and experience. We also extend our sincere thanks to our panelists for their valuable contribution and thoughtful discussion. Thank you for being part of this session. See you.
Thank you, Dr. Segarra. Okay.
Thank you.
Now at this moment, we are going to present a digital certificate of recognition to Professor Wieman, conferred by the National University of San Marcos in acknowledgement of his distinguished participation in this international conference. Here we have, this is for you, Dr. Wieman.
Thank you.
Please, class for him, yes. Thank you, Dr. Wieman, for your invaluable participation today. Okay, now, prior to concluding this session, I would like to invite our panelists, organizing committee, and Professor Wieman to kindly activate their cameras for a group photograph. Okay, we will capture the image in a few minutes. Thank you.